Okay, so in this video I'm going to be finishing section 12.2 and then we'll be moving on to 12.3 in this video. So in the last time we met we were finishing we were in the middle of 12.2 talking about how to put a matrix in row echelon form. And so we went over these steps to obtain a matrix in row echelon form. And then once we get a matrix in its row echelon form, we can find the solution to the original system of equations. So I have already went over with you how to do those row operations. So for this first example here, I'm actually going to show you how to do it on a calculator. So first, let's put this system of equations into the augmented matrix. So we see that the coefficients of the first equation are 1, 1, 1, and then it's equal to the constant -4. And then for the second equation, we have 2x, 1y, and then no 0. So we would have 2, 1, and then 0. And sorry, I didn't mean to say no 0. I meant to say no z coefficient there. No coefficient for z, so that would be 0. And then this is equal to the constant 0. And then finally for the last one, we have 3x minus y minus c is equal to 8. So that would give us 3, -1, -1, and 8. So I am going to go to, let me take a picture. To the TI-84 and show you how to enter the matrix into your calculator and then get the row echelon form of the matrix. So you're going to hit the second matrix button, which is the 4th button down below second, right there. And it brings you to this screen, and you're going to want to hit the right arrow over to edit. And then it's already selected on the first matrix A, so you can just hit enter. And then it's going to ask you to enter the dimensions of the matrix. So remember, the rows always come first. And this was a 3 by 4 matrix. And then hit enter. And then it populates this 3 by 4 matrix for you. And we can go and enter each entry in now. So it's highlighted on that first entry of 0. And I want to change that to a 1, so I would click on the 1 and then hit enter. 1, enter, 1, enter, 4, or sorry, -4. -4. Okay. And then 2, 1, 0, 0. And then 3, -1. -1, and 8. Okay, so I've entered in this matrix, and usually to get out of this screen, because it's kind of weird, I just click on graph, and then I hit clear to get back to the original screen. And now, to find the row echelon form of that matrix, I'm going to go back to second matrix, and I'm going to go over to math. And I'm going to go scroll all the way down until I see that REF, just one R, REF. And I'll click enter. And then it puts the REF notation on my calculator screen. And now I need to enter the matrix that I just put in. So I'm going to hit second matrix again. And it's highlighted on the matrix A there that I just created, the 3 by 4. So I hit enter. And I can close those parentheses, and then I would hit enter again, and it gives me the row echelon form of this matrix. Now it's giving me some of these entries in long decimals, so I can actually convert these back to fractions by hitting the math button. Hold on, I don't know why this. Okay, math, and then fraction. It's already on fraction. Hit enter and hit enter again, and now it'll give you the matrix in fraction notation. So this is the row echelon form of the original matrix, and I'm going to go back to my screen here. Okay, so on this page here, I've written down the instructions on how we just got the row echelon form using the calculator. So I put those instructions here. And now I'm going to write down that row echelon form that we got. Okay, and from here we can build out the equations. We can rewrite the actual system of linear equations using this matrix, but because I have a lot of fractions and I'm trying to solve the system now, so this is the row echelon form, but if I wanted to solve the system, maybe I want to get rid of those fractions, so I can multiply the first row by 3, which will give me 3, -1, -1, then 8. And then I can multiply the second row by 5, which would give me 0, 5, 2, -16. And then the last row is fine. Okay, so now we see that from the last equation, well, I'll just build out the entire system from this. So this is equal to 3x minus 1y minus z is equal to 8. And then 5y plus 2z is equal to -16. And the last one says that z is equal to -3. So I can actually use this z value here and plug it into this z to find the y from the second equation. So this would be 5y plus 2 times -3 equals -16. And so now we would be doing the step of back substitution. Into equation 2. So that would give me 5y minus 6 is equal to -16. I would add 6 to both sides, so that would give me -10. And so y would equal -2. So now I have a value for y as well. And finally, I just need a value for x. So I will use the first equation and plug in both y and z. So this would be 3x minus -2 minus -3 is equal to 8. Which will give me 3x plus 2 plus 3, so plus 5. subtract 5 over, so 3x is equal to 3, so x is equal to 1. So therefore, the final answer just make some room here. Would be the 0.1 comma -2 comma -3. So that would be the solution to this system. So they also have showed you how to do it using the row operations. And when you do the row operations, you do get a nicer form for the row echelon form than you would your calculator, but just well, if you did the steps that they did. Of course, there is multiple different steps you can take to get a matrix in row echelon form. So it's possible to get different forms that will still give you the same solution. But they did the row operations and got it in row echelon form, and they found the same answer. 1, -2, -3. And they also showed their row echelon form that they got in the calculator, which is the same as what we got in the calculator. Okay, so I'm not going to go over that. Okay, so this next example, we are going to learn what it means for a system to be dependent. Okay, so this is a system of equations in 3 variables. So I can solve this system of equations by putting it in matrix form. And the augmented matrix is given by this matrix here. So on the top, I have 3x minus 3y plus 6z. So that is my coefficients. And then it's equal to the constant 3. And so on. The next one, 2, -4, and then 8, -8, 11, -4, and then -17. So that's the augmented matrix. And then I'm going to start taking steps using my row operations to get it in row echelon form. Now you could use your calculator to do this as well, but I'm just going to go over the row operations with you one more time. So remember, the first step is to get the first entry equal to 1. So I can divide the first row by 3. So that's the notation there. I get a new row 1 by dividing the old row 1 by 3. So I get 1, -1, 2, and 1 for my new row 1. So then I accomplish that. The next step is to get the number below it equal to 0. So I can use this 1 here, multiply row 1 by -2, and add it to row 2 to get that to be equal to 0. And so that is what they are doing here to get this new row 2. So this was where we were at previously, and remember I said I can multiply row 1 by -2 and add it to row 2 to get a new row 2. So -2 times 1 plus 2 is 0. -2, sorry, let me erase this so I can. -2 times -1 is a +2, plus -4 is a -2. And then -2 times 2 is -4, plus -4 is a -8. and then negative 2 times 2 is negative 2, plus 8 is a positive 6. So that's how they got row 2. And then they actually do 2 steps within this row. The next step they're going to do is they are going to try and get this one equal to 0 as well. So they multiply row 1 by a positive 8. And then they add it to row 3 to get a new row 3. So 1 times 8 plus negative 8 is 0. And negative 1 times 8 is negative 8, plus 11 is 3. And then 2 times 8 is 16. 16 plus negative 4 is 12. And then finally, 8 times 1 is 8, plus negative 17 is negative 9. So that's how they got row 3. Okay, so now we've gotten the first entry equal to 1 and all the entries below it equal to 0. So the next thing I would like to do is get this entry equal to 1. So I can easily divide row 2 by negative 2 in order to get that to equal 1. And so that's what I'm doing here to get my new row 2. So negative 2 divided by negative 2 is 1. Negative 8 divided by negative 2 is 4. And 6 divided by negative 2 is 3. Negative 3. Okay, and then the next step to continue to get row echelon form is to get this 3 to equal 0. So now I can multiply row 2 by negative 3 and add it to row 3 to get a new row 3. And that is what they are doing here. So negative 3 times row 2 plus row 3 to get a new row 3. So negative 3 times, negative 3 times 0 is 0, and 0 plus 0 is 0. Then the next one is negative 3 times 1, which is negative 3, plus 3 is 0. Then the next one is 4 times negative 3, which is negative 12, plus 12 is 0. And then negative 3 times negative 3 is a positive 9, plus negative 9 is 0. So that one actually creates all zeros in my bottom row, which is fine. But now this is in row echelon form because the first entry is a 1. Everything below it is equal to 0. The second row, the first non-zero entry is a 1, and everything below it's equal to 0. And then the next row, they're all equal to 0, so that's fine. So there is, this is in row echelon form, and we can actually build this in its system of linear equations form. So I'm going to do that down here. So the first equation would be 1x minus y plus 2z is equal to 1. And then the next one is 1y plus 4z is equal to negative 3. And then the last one is all zeros, so I don't need to write that. So this would be my new system. And if you notice, in all the previous examples we've done, we've gotten a value for one of our variables, but here we do not. So the first equation is x, y, and z, and the second equation is y and z. So when this happens, you get a free variable, what we call a free variable, which means z can be anything. And then x and y would be dependent on z. So I'm going to solve both of these for z. I'm going to start with the first one. So y would be equal to negative 4z minus 3. And then the next one, for x, I can plug in what this equals for y, into this equation. So this would be negative 4z minus 3 plus 2z equals 1. So I solved the second equation for y, and then I plugged that in for y into the first equation. So I can get everything in terms of z. And so this will give me x plus 4z plus 3 plus 2z equals 1, which will be x plus 6z equals to negative 2, so x is equal to negative z minus 2. So I just solved that for x. Okay, so, and I'm going to actually erase this because y'all know how to solve equations. So I'm going to rewrite now what I just did. I solved I solved this second equation for y, and then I plugged that into the first equation and solved this for x. So this would actually be the solution where z can be any number, but y has to be equal to negative 4z minus 3, and x has to be equal to negative 6z minus 2. That's what they do there and there. So this is actually an infinite amount of points as long as x and y is equal to this. So here is the solution written in set notation. So this would be the set of all ordered pairs such that x is equal to negative 6z minus 2, y is equal to negative 4z minus 3, and z can be any real number. So this is how we could write the solution to this system. Now this system is called dependent because it does have a solution, but it has infinitely many amount of solutions. And the solutions depend on z. Depends on what z is. But z can be any real number. Okay, so this is called consistent system, and this is the solution. So anytime that you get your matrix in row echelon form, and you don't have one of the variables specifically solved for like a number, you just want to always solve x and y in terms of z, and then write your answer that way, where z can be any number. Okay, so now we're going to do another example and see what happens, how we can tell whether a matrix or system is inconsistent, meaning it has no solution. So I have the augmented matrix here from the system above, and we're going to work on getting this in row echelon form, or you could use your calculator. So the first thing they do is they interchange rows 1 and 2 here to get this system. The reason why they do that is because row 2 already has a negative 1. So if they just interchange those two rows, then I can easily just multiply row 1 here by negative 1, and I'll already have the first entry be a positive 1. which is the first step in getting a matrix in row echelon form. Okay, so that's what they did here. They multiplied row 1 by -1 to make it positive. And now, of course, they're going to multiply row 1 by -2 and add it to row 2 to get a new row 2. And that's what we see right there. And then they will multiply row 1 by -3 and add it to row 3 to get a new row 3. And in order to get these two to be 0 here. Okay, and then it actually worked out pretty nicely where this is already a 1, so I don't have to worry about that. So the next thing I want to do is get this equal to 0. So I will multiply row 2 by -2 and add it to row 3 to get a new row 3. Okay, so now this is in row echelon form, but you see here that, well, it's not really in row echelon form because this is the first non-zero and it's not 1. But from right here, you can see that this says that 0 is equal to -4, right? This would be 0 times z is equal to -4. Or even more precisely, it would be 0x plus 0y plus 0z is equal to -4. But this is impossible. 0 can't equal -4, so this is false. So there is no solution. There would be no solution to this system. So it is inconsistent. So if you get your matrix down to where everything is equal to 0 on the left, and then you still have a number on the right, that is going to be inconsistent. All right, I'm going to skip this example here because you can see, what they do here. You can read that for yourself in the notes. But I am going to go over this word problem. So this says that Adam and Michelle require an additional $25,000 in annual income beyond their pension benefits. They are rather risk averse and have narrowed their investment choices down to treasury notes that yield 2%, treasury bonds that yield 3%, and corporate bonds that yield 6%. They have $700,000 to invest and want the amount invested in treasury notes to equal the total amount invested in treasury bonds and corporate bonds. How much should they place in each investment? So first of all, they said that they have $700,000 to invest, and they're investing this into 3 accounts. So if I let N represent the number invested in treasury notes, and B be the amount invested in treasury bonds, and C be the amount invested in corporate bonds, well, all 3 of those should add up to the total amount that they have to invest. So this is where I get my first equation for my system of equations. And then the second one comes from the percentage per note or bond. So they said that the treasury notes yield 2%, so they'll gain 2% off of their treasury notes. Treasury bonds gain 3%, and corporate bonds gain yield 6%. So if I wanted to gain they require an additional $25,000 in income. They want this these three bonds and the treasury bond and the treasury note and the corporate bond, they want the amount that they gain from those three accounts to add up to that $25,000 that they require for an additional income. So I can find the amount that each account earns them by multiplying the amount that they invest by the percentage of the bond. So if N was the amount for the treasury notes, and it says that the treasury notes yielded 2%, so that would be 0.02 times N. And then it was 3% for the treasury bonds and 6% for the corporate bonds. So the sum of all of those three should equal the total amount gained from these investments, and I want that to equal 25,000. So this is where I get my second equation from. And then the last piece of information they gave me was that they want the amount invested in treasury notes to equal the total amount invested in treasury bonds and corporate bonds. So that means that they want the total amount of the treasury note to equal the total amount of the bonds and the corporate bonds. So that would give me N is equal to B plus C, or if I got this equal to 0, that would be N minus B minus C equals 0. And so here are my three equations. And I could use my calculator and plug this in as the augmented matrix, like this. Or I could do it by hand and use row operations, but I just need to get it into row echelon form. And down here we see that they do get it into the row echelon form. And they find that Z is equal to 250,000. And if you remember, well, yeah, it was C. That was representative C. If you remember, these represented N, B, and C's. So C was the amount in the corporate bond. So that means that C is equal to 250,000, the amount that they had invested in the corporate bond. The next equation says that B plus 4C is equal to 1,100,000, and I can plug in the 250,000 into that and solve for B. And I am just going to go here where they do that. And that's going to give us that B is equal to 100,000. And then when you back substitute that into the first equation with the 250,000, you get that N is 350,000, which should be invested in the treasury notes. Okay, so that's the end of 12.2. So I am going to move on to 12.3. And we're going to talk about how to find the determinants of matrices. And we're going to start with the most basic example of finding the determinant of a 2x2 matrix. And so if I have a 2x2 matrix, and this matrix looks like this, then the determinant of that matrix is denoted like this, either with a capital D, which is equal to the determinant of this matrix, this is the symbol. So this symbol literally just means the determinant. We haven't actually taken the determinant. But in order to find the determinant of that matrix, it is the difference between the products of the diagonals. So you do A times D minus C times B. So this is actually the determinant, this calculation. But the notation with the straight up and down bars, it looks like an absolute value bar. That means to take the determinant, notation. Okay, so for example, the determinant of this, and just so you know, again, they're already using the straight up and down bars. So this is not, this is asking me to find the determinant of this 2 by 2 matrix. So this would be equal to 4 times 2 minus 7 times negative 1, which would be 8 plus 7, which would be 15. Okay, and now I'm going to show you how to do this in your calculator. So if I go back to second matrix and I go back to edit and I go 2 by 2 matrix, and I already forget what it was, 4, negative 1, 7, 2. So 4, negative 1, what happened? Sorry, go back to edit. Okay, 4, 1, negative 4, negative 1, 7, 2. Seven, 2, and I need to change that to a negative 1. Okay. Alright, so I entered my matrix. Now I can go to back to second matrix and go to math. Click on determinant and then click on second matrix and click on that matrix you just entered. Hit enter. And then it'll give me the answer, 15. So your calculator, I believe, will only give you the determinant of a square matrix. So like 2 by 2, 4 by 4, 6 by 6, but not of a non-square matrix. Okay, so this theorem is the theorem regarding Cramer's rule, and specifically the first thing we're going to learn about is how to use Cramer's rule to solve a system of equations containing 2 equations and 2 variables. So of course I could solve this system using elimination or substitution method like we've learned in the past. But I'm just going to show you that there is another way to solve this by using the determinants of matrices now. Okay, so what this says is that the solution to this system, if you remember again, is a ordered pair, x comma y. So for the x coordinate, this is equal to the determinant of this matrix here, which is SBTD, and if you notice, they are replacing the coefficients for the x terms by ST here, and then they have BD. Okay, I'm going to explain that a little bit more too. And then it's divided by the determinant of the coefficient matrix, which is here, A, C, and B, D. That's just the original 4 by 4 matrix of the coefficients of the variables. Excuse me. And then the y-coordinate of the solution is given by the determinant of the matrix, where we replace the y-coordinates by st. So this is AC, which comes from the x-coordinates, and then st. So instead of the coefficients in front of the y terms, we put the constants there. And it's still divided by the same matrix of the 4x4 matrix of the coefficients of the variables. So, provided that the determinant of A, B, C, D is non-zero, then we can use this to find the solution to a system. But of course, these cannot be zero. These cannot be zero because they're in the denominator of a fraction. This is a determinant divided by a determinant. That's what that notation is. Here's another way we write it. The x is equal to the determinant with respect to x divided by the determinant d. And y is equal to the determinant with respect to y divided by the determinant d. When I say with respect to y, that's what I mean. I mean we are replacing the y terms here with the constant terms. So let's see an example. Okay, so first, the d, again, comes from the coefficients of the variable terms. So the d matrix would be 2, 3, 3, negative 2. And so to find the determinant of that, that will give us d. And that would be 2 times negative 2, which is negative 4, minus 9, because 3 times 3 is 9, and that will equal negative 13. Okay, so d is equal to 13, or negative 13, which is non-zero. So that shows that we can use this Cramer's rule to find the system of this equations. So the next thing we're going to do is find the x coordinate by finding the derivative with respect to x divided by, did I say derivative? The determinant with respect to x divided by the determinant of d. And we already found d to be negative 13. So we already know what d is. But d of x is going to be the determinant of the coefficients, except for I'm replacing the x coefficients with the constant coefficients. So that'd be 121, and then the coefficients of y stay as is. So I'm finding the determinant of this, which would be 1 times negative 2, which is negative 2, minus 63, and this would be negative 65. So the x coordinate would be negative 65 over negative 65 over negative 13, which gives me a positive 5. So that's my x coordinate. And then the y coordinate would be equal to the determinant, or I'm sorry, the determinant with respect to y would be equal to the determinant of 2, 3, and then replacing the coefficients of the y terms with the constant terms, which would be 1 and 21. So this would be 42 minus 3, which would be 39. So the y coordinate would be 39 divided by negative 13. which is -3. So the final answer, which is an ordered pair, is equal to 5, -3. Okay, so this is a way we can use Cramer's rule to solve for a system with 2 variables and 2 equations. All right, so far we have only learned how to find the determinant of a 2 by 2 matrix, and now we're going to talk about how to find the determinant of a 3 by 3 matrix. Okay, so this is the notation here, and I'm going to kind of spell this out. So I will say, when you find the determinant of a 3 by 3 matrix, you always start by picking one row or a column. Like I could pick this row, or I could pick this, or sorry, the last one was a column. I could pick this column, or I could pick this row, or I could pick this column, or I could pick this row. Doesn't matter. But for the purposes of teaching this, we're going to mainly stick with the first row. But again, the process, you always start with one of them. You just pick one row or one column. So I'm going to pick the first row, and then I'm going to start with the entry on the left. And so that's where they get A11 from. And it will be that entry, whatever number is there in the first entry, times, that's why it's right next to this symbol here, the determinant, because notice these are up and down bars, so absolute bar, well, it looks like absolute value, but it means the determinant of the matrix that's left after you cross out this row that first entry's on, and you cross out the first column it's on. So you see that leaves me with this matrix here. So that's the determinant of that matrix. And then you move to the next term. Okay, so we started with A sub 1, and now I'm moving to A12. A sub 1, 1, sorry, A sub 1, 2. And the next term will be multiplied by A sub 1, 2, but the signs have to alternate. So first it was positive, and then it was and then it's going to be minus for the second one. So this would be minus A12 times the determinant, again, of what's left after you cross out the column and the row that's on. So that would be the A213 and the A23, A33. So that's the 4 by 4 matrix that's left. And then again, the sign changes, so this becomes plus again. And we move on to the last entry of the A sub 1, 3. And this gets multiplied by the matrix that's left after you cross out the row and the column that entry's in. Okay, and then of course we would find the determinant of each of these and simplify. Okay, so first of all, before we do an example with this, we're going to talk about finding minors of a 3 by 3 determinant. So minors are going to be kind of like what I just explained. So for example, they want me to find m sub 1 of 3. This means that, or m sub 1 of 3 is the determinant that results from removing the first row and the third column from A. So I remove the first column and the first row and the first column. I'm sorry, first row and the third column. And so that leaves me with this 4x4 matrix here. And that this notation tells me to find the determinant of that. So then I find the determinant of that, and that is equal to 26. Okay, and then M sub 3 is the determinant that results from removing the third row and the third column from A. So you see they crossed out the third column and the third row, and that will just leave me with the determinant of -1, 3, and 4, and -2, which is going to be equal to -10. Okay, so determining whether these signs are positive or negative within this, when you're finding the determinant of larger matrices, this is called the cofactor. And so we actually call that process of finding that matrix, or those determinants, we call that the cofactor expansion. And so the definition of the cofactor is for an n by n determinant A, the cofactor of entry A sub ij, denoted as capital A sub ij, is equal to -1 raised to the I plus j power times m to the times m sub ij, where I is equal to the row number and j is equal to the column number. So for example, did it say this? Oh, okay. So let's do this example here. So we're going to find the determinant of this 3x3 matrix. So they are choosing to use the first row. So this entry 2 here, this is entry A sub 1, 1, because it's in row 1, column 1. So for the cofactor, excuse me, I'm trying to rewrite that. Cofactor A sub ij is equal to the -1 I plus j power times m to the ij. So this means the first cofactor of that entry. Okay. So this is just going to give us the value here. And this will be 1 for I and 1 for j. So this will be -1 raised to the 1 plus 1 power times 2, because that's the first number there, times the derivative of what you get when you mark out the first row and the first column, which will leave us with this. Okay. Then the next one, so anyways, -1 to the 1 plus 1 power, this will be -1 squared, which would be a positive 1. Like I said, it starts positive. This one's going to be negative because now we're moving on to A sub 1, 2. So this would be -1 to the 1 plus 2 power, which would be -1 cubed, which would be -1, times 5 times the determinant of the matrix where row 1 is canceled out, and column 2 is canceled out, which leaves me with this. And then finally, we move on to the last row, or last entry on that row, which is 0. So all of this would just be 0, but this cofactor would be -1 raised to the 1 plus 3 power, because that's in the first row, third column. Okay, so that'll just make it, or this will make it a +1, because that'll be an even power. And now we will go through and evaluate. So the first one, again, will give us a +2 out of all this, times the determinant of that matrix. So let me use my, so this would be 2 times the determinant, -1 times 6, which would be -6, minus a -8, minus 5 times 18 minus 20. And then the last one is just 0. So after evaluating that, we get that the determinant of this matrix is equal to 14. Okay, I'm going to stop the video here and take a quick little break, and then I will finish with the rest of this in a minute.